So in our parametric equation here, as we change the value of t, that is change the value of our parameter, we should get different pairs of x and y points. So let's see what those look like. If I plug in 0 into the x coordinate, or the expression here for x, what will I get? What's 2 times the sine of 0? Well, sine of 0 is 0 times 2 is still 0. How about if I plug it in for y? Well, cosine of 0 is 1 times 3 would be great. All right, so let's keep going. Let's plug in pi over 2 next. Sine of pi over 2 is, let's roll with these. 1 times 2 would be a 2. Cosine of pi over 2 is 0.
0.
Times 3 is still 0. Let's move over to pi. Sine of pi is 0. Times 2 is still 0. What about cosine of pi?
1. Negative 1.
Negative 1. So I'll end up with a negative 3 here. And just a couple more. Sine of 3 pi over 2 is negative 1 times 2 is negative 2. And then 0. And finally back to 0 and 3 where we started. So this is starting to repeat itself. So what does a graph of that look like? Well, it looks like this down here, but there's something interesting about the way this graph gets traced out. The way it gets traced out, starting with t equals 0 all the way up to t equal 2 pi, gives it an orientation. Notice that we started out here with the point 0, 3. So you start up here, and then which way did we move? Well, we moved around to 2 and 0. That's on the x-axis. And then we moved to 0, negative 3. That's down here. And then the negative 2 and 0. And in general, we started here and we moved in this direction. And the direction in which this is traced out is called the orientation for this graph. That's something that I'm going to ask that you give me on an exam. Is, well, what's the orientation of this curve? How is it traced out? Now let's see how that works in your graphing calculator. So first of all, let's check our mode. Our mode should be in parametric mode. If it's not, just go down, go over and press enter on parametric mode. One other thing here, do you think I want to be in radians or degrees for this?
Radians.
Radians. So let's go over and make this in radians. Oops, I don't think I got that in radians. So radians. And finally, when we go over to our y equals key to enter our equations, it's going to look a lot different than what we're used to. That's because it's giving us the possibility of drawing an x and a y. So, all right, great. So our x coordinate was 2 times the sine of x, or when we press our old trusty x button, we don't get x anymore. What do we get?
T.
T. That's because we're in parametric mode. So, all right, we're going to get a t when we press this thing now until we change back to function mode or some other mode. 3 times the cosine of t. Great. Now comes the time to setting up our window. Now, I guess one way to do it is just to let your calculator kind of do all the dirty work for you. And that is, we'll set t to go between 0 and, what's this number, 6.283? You want to tell me what that is?
2 pi?
2 pi, exactly. Excellent, thank you. So 2 second pi. Now when I press enter, that pi symbol is going to disappear. It's going to be replaced by the decimal value. That's okay, it's still 2 pi. T step. So what's going to happen is, when we graph this, I filled in a lot of spaces. But when your calculator graphs this, it's going to start out at t equals 0, and then add whatever t step is, maybe 0.05, and then it'll plot the next point, and then the next point, and the next point. Now you don't want this too small, you don't want it too big. So what do I mean by that? Let's start by setting, say, t step equal to 1, and just see what happens. Now for the rest of this, I'll let the graphing calculator, actually, we don't need to let the graphing calculator do it in this one, because we already know that I want to go from, say, -3 to 3 on the y-axis and -2 to 2 on the x-axis. Let's go a little bit farther. Let's go from maybe -4 to 4 on the x-axis. That'll keep this graph in shape. So -4 to 4 on the x-axis and -3 to 3 on the y-axis. You can go a little bit farther if you'd like on the y-axis so that the graph is fully inside of your window. And now,
Ew.
it doesn't look too good, does it?
Ew.
That's because it plotted the first point, and then it went to the second one, and then the third one. It only gets up to 6 points. Let's make that a little bit smaller. Maybe t-step is 0.5. And that looks a little bit better. In general, what I found is that a t-step of, say, 0.1 or better yet 0.05 works pretty good for most situations. So if we graph that, and there you go. Now, are you getting this cool little tracer item on your graph that I am on mine? No? No, all right. Let me show you yet another cool graphing calculator trick. So if you go to the left of your equations, you can choose the style of equation that you want. So when I press enter, I can choose the color of line that I want. Blue is an awesome color, so we'll keep that. But then I can choose the style of the line. So when I come down here, I can move to the left, and I have all kinds of different styles of line. That's your basic line. That one's kind of boring. That's a thicker line. Back when this calculator used to be in just black and white, I would use thick and thin lines, and then lines that were dashed and dotted. This is what you want. You want this circle with a little line to the left. Choose that one, then come down and press OK. You have to press OK here, otherwise it won't make that change. That'll put this cursor on your graph, and then you can watch it get traced out. So there you go. Now you can go a little bit overboard with the step size and it not work out too good. If I go back here to my window, if I make this say 0.001, then boy, it's like watching paint dry to see this thing move. All right, that's just too many points. So it's just taking its sweet old time. I don't know why they didn't put a more powerful processor in this. They've had this thing for decades, so time to upgrade.
So
In my humble
0.05
opinion.
should be good.
Yeah, 0.05 should be pretty good for most of these. Now I'm just going to press the on button here to stop that and go back to my window and fix it. 0.05 is probably a good happy medium in which to leave it. So 0.05 like that, and then bam. That's reasonable. So it gives you a good enough level of detail without taking forever to graph. Nice, nice. All right, so I think there's a Desmos link on D2L with this. So let me just see if I can't follow it. And those of you who are here, up close and personal, I think you can follow the QR code that's there as well. Try and jump on that. Let's see. There's Despicable Me. This is the one I want. Okay. So it should look like this. And I want to try and answer the second question. Determine if the below statement is true or false. Parametric equations defining a curve are unique. That means if you got one curve, there's only one way to define it. Well, let's take a look here. Let's start by looking at this parametric equation. And maybe I'll zoom in a little bit. Let's try and make that a little darker. There we go. So there's one parametric equation. I've got these pairs of points. What about if I did that pair of points? Oh. Well, the first one's the top half of a circle, the second one's the bottom half of a circle. Okay. But what else could I do? I could do sines and cosines. Now that's only a quarter of the circle, but how do you think I could get that to extend all the way around the circle, do you think? Maybe let's change that to, I don't know, a 0. Or I could use this one. So what do you think? Let's go back to the question that was asked. Parametric equations defining a curve are unique. What do you think? Is there just one way to define a parametric equation? Shay, what are you thinking? True or false?
I think that's true.
Well, let's take a look back here. That's a circle, so I defined it one way. These are different equations. I'm still getting this a circle. Again, these are different equations. These two give me a circle. So do you think there's more than one way to do a parametric equation? Seems that way. Yeah, I've got several right here that are all giving me a circle or part of a circle. So the problem, one of the challenges of working with parametric equations is that their graphs are not unique. So false.
Oh, fault. Unique means just one way.
Yeah, there's just one way. You're unique. Although it's kind of funny, one of the things in the English language is to say, oh, you're very unique. And the thing is, you can't be very unique. It's like being pregnant. You're either pregnant or you're not pregnant. You're not very pregnant. Although people do use those kind of things, but it's just you're unique or you're not unique. So that's it. In any case, let's move on down to example C. So it says, graph the curve whose parametric equations are given below. Find the rectangular equation for the curve. Now the rectangular equation is kind of interesting. Because for the rectangular equation, what you want to do is you want to get rid of the t. You don't want this to depend on that parameter, on that thing that varies. So let's start by doing that, getting rid of the t. So I've got x equals t squared plus 2 and y equals t squared minus 2. How do you think I could work with these and get rid of the variable? Any suggestions? I can think of a couple ways.
I think it's just y.
Oops, yeah, it is just y. Thank you. There you go. There's just some dust on the lens. All right, thanks. How can I get rid of the variable here, the t?
System of equations?
Yeah, you could use the addition method. You could use substitution or addition. For instance, if I move the 2 to the other side, I get y plus 2 equals t squared, right? And then I could take this expression and substitute it in for t squared here. So it would be x equals y plus 2 again, or in other words, x minus y equals 4, moving the y to the other side and combining like terms there. And that's beautiful. That's exactly what I was looking for. I was looking to get rid of the variable, or the variable t in this case.
Wait, how did you distribute that? I'm kind of confused.
I didn't distribute. I just don't need the parentheses here. Are you okay with?
Oh, wait a minute. I was worried because of the parentheses. That's why.
Yeah, but there's no distributing. It's just, I took off the parentheses and added those 2. 2 and 2 gave me the 4, and then I moved the y to the other side.
All right.
Great. You could put this in slope-intercept form. You could do y minus or x minus 4 equals y, and then graph it. So that's going to be something down here with a y-intercept of -4 and an x-intercept of +4, and then a line at a 45-degree angle from there. So there's our graph. But what would that look like if we tried to do it in parametric mode? No, okay, let's do that. So in parametric mode, I've got to change my equations. And the first equation was x is t squared plus 2. So t squared plus 2. Second equation is y equals t squared minus 2. Now the thing about parametric equations is that they don't always exactly match the equations that you have in x and y. Sometimes they'll only give you part of that. And that's going to be the case here. What do you know about something when you square it? When you square something, what happens to that variable? It's always what sign?
Positive.
It's always, yeah, it's always positive. So what that means is that, you know, for whatever this graph looks like, I'm not going to get anything less than 0 in the x direction or less than 0 in the y direction. So my graph, I think the smallest I'm going to get is, well, let's see. No, actually I can get down to -2. So yeah, I'm not going to be able to get all of this line with this parameterization. Different parameterizations will give you all that line. All right, let's set up our window. Now, let's see. Let's go from 0 to 10. And then we'll let our calculator do the rest.
Mr. Joe,
Yes.
can you just click on zoom and do zoom fit? The calculator will automatically give you the right window for it.
That's what I was going to do on this one. But you need to set up your Tmin and Tmax first. So once you have those set up, then your calculator should be able to set up the rest. So Hamza's question was, can't you do zoom fit? And the answer is yes, but you have to have Tmin and Tmax set. So I'll do zoom and then 0, that is zoom fit. And boy, that's pretty ugly. See, this is the problem with zoom fit, is that it always, you know, it can do kind of strange things like that. And maybe I don't want to go up to t equals 10. Because now that I think about it, t equals 10, 10 squared is 100. That's getting kind of big. I don't want to see it all the way out there. So let me change this up a little bit. Let's go from, say, -5 to 5. See if we get a better window and do zoom fit from there. So zoom 0. That's looking a little bit better. Bam. Now notice what's happening. My cursor went all the way down and then it started going back. Okay, so it traced out more than it actually needed. That's okay. But this is about as far as you're going to be able to get down here, is this point, which is I think at 2 and -2. And that'll happen when t equals 0. If I just make this a 0, I don't think I'll get that retracing. It's just going to trace it out in one direction, not both. There. Okay. But the bottom line with that graph is you're never going to be able to get down past 2 and -2 as a point. That's it. That's as far as we can go. So is this the same as the graph in x and y coordinates? Not exactly. Not really. It's kind of close, but it's not ever going to get past where we're at here. Ben?
They go back and forth because you use -5.
So the reason it's going back and forth when I typed in the -5 is because each of these terms here has a squared. So if you're squaring 5 or squaring -5, you're going to get the same thing. So it starts out at -5 and squares it, and then the numbers increase until you get to 0. And then you're going to start seeing repeat, because when you square positive 5 or you square positive 2, you get the same thing you get when you square negative 2. So this one should actually repeat itself, whereas if I go just from 0 to 5, it won't. So good question. Good question. Okay, let's keep going. Parametric equations are kind of cool. And I'll show you a nice example of where you use those in the next one. But let's work with example D here. It says graph the curve whose parametric equations are given below. Find its orientation. Let me highlight that. Find its orientation. Or show its orientation. That's showing in what direction the graph gets traced out. Find the rectangular equation of the curve. All right, so that's what we did just up above in example C. So that's another part. Both of these are good questions for an exam. Label the orientation of the curve. All right, let's start by figuring out what this looks like in terms of X and Y coordinates. Because even for me, it's hard for me to think in terms of parametric equations. I can't visualize these things as good as I can with X and Y equations. So what would you suggest? How would I get rid of the variable here? What's the easiest way? Substitute. All right, sounds good. Substitute what into what?
5t.
Like substitute, you make t equal y minus 2 and you take that.
Beautiful.
To the t squared.
The easiest thing to do is, like Hamza said, and that is get the t by itself. And once you have t by itself, you can substitute that expression into the other equation. So that means y minus 2 equals t, and that I can put in here, x equals 5 times y minus 2 squared. So for my college algebra students who happen to be here as well, what's the graph of that going to look like? A parabola.
Rounding.
Yes, nice. And that parabola is going to face which direction?
And down.
Is it upwards?
Sideways. It's a parabola on y squared. So it's going to face sideways. Oh, man. All right. We'll quiz you on the focus and directrix later. But so for right now, this is a parabola that faces sideways. Let's plug in some values for t and see what we can get in terms of, tracing out this curve. Now, eventually t is going to go from negative infinity to infinity. Let's start out with a modest negative 5 to 5 and see what this graph looks like. So let me clear out a couple of the old things, put in the new. So I want 5t squared, that's my x value. By the way, because of this, that's telling me my x's will never be negative, because 5t squared can never be negative. And finally, my y coordinate is going to be t plus 2. T plus 2. For my window, I've got negative 5 to 5, so I'll stay with that. Zoom 0. And wow, kind of messy here on the x-axis, isn't it? But there's our parabola. Vertex at 0 and 2. Okay, that looked pretty good. Let me see why I'm getting that big mess of things on the y-axis or on the x-axis. That's because the x-axis goes up to 125, and I'm trying to put tick marks every unit. That's why I'm getting such a mess here. To clean that up, let me put tick marks at something a little bit bigger, like every 25 units, something that evenly goes into this number. And now we'll look at the graph. That looks a little bit more readable. You just got to keep in mind that that's 25, 50, 75, 100, 125. So a little bit easier to read. What am I going to want on an exam? Well, good question. So first of all, you should be able to draw the graph. The important feature of the graph is that it has a vertex here at 0, 2. Let's see. Probably the other point that I might be a bit of a stickler about would be the x-intercept. And it looks like it's crossing the graph at maybe, I don't know, where would that be? 20. Yeah, that'd be 20. So, yeah, that's too big. Let's see, 20.
Hey Jeff,
Yes,
sorry to interrupt, but would it be possible to record this?
I am recording it.
You are? Okay, thanks.
Yep. All right. Let me turn this down a little bit for a second. There we go. You know, in looking at this, I don't think I did a good job of giving you a graph here because the x-intercept is way out here. This would be a really skinny parabola. So somewhere out there, it's actually around x equal 20. That's going to cross the, so 20 and 0 is where we cross. All right, but let's work on the orientation here. The orientation is the way the graph is traced out. So I've already got this graphed. It's not going to graph things again unless I make some kind of a change. So let me make a change this way. I'll just make this 0.1 instead of 0.05. It'll graph a little faster, still should be pretty good. But you see the order in which this is being traced out. The graph starts literally right here and goes this way. That's its orientation. So you've got its equation in terms of x and y, you graphed it, and you've shown the orientation. Hopefully, I mean, other than this might be a little bit tricky, hopefully the rest of these are easy points for you, all right? I'm not trying to trick you on this. This is exactly the kind of thing that I'm gonna ask. Now, something that I remember a young Jeff parent asking of his instructor one time is, where do we use this stuff? And to my dismay, my instructor didn't have a good answer. I like to have good answers for you. I like you to know that people actually do use this stuff, especially in an automotive town like this. Can you imagine a point on the rim of a wheel? If that wheel is moving forward, what's the graph of that going to look like? Well, the graph would look like what's called a cycloid. So if you happen to have this open, I think I've got a link here that should take you to the graph of a cycloid. So let me see if I can open that up. And that helped, let me see. All right, it's doing something. It's not what I'm controlling.
Press middle mouse, the middle of the screen.
Press what?
The middle, like, just pushing the scroll wheel.
Oh, the scroll wheel, there we go.
And then cancel.
It's still doing kind of what it wants.
Push the scroll wheel in again.
Yeah.
I think it's broken.
See,
Oopsie. Yeah, I don't have a touchpad on this either. So if the mouse is broken, I'm in real bad shape.
I don't think it's the mouse. This is just all the thing.
So there's a problem someplace between the keyboard and the floor. All right. No, the mouse is working okay over. But there we go. Let's see. Come on, over. All right. It's working now. Let's see. Here we go. So if you do follow that link, here's what's called a cycloid. And it's just a point on a rim rolling, you know, endlessly. And I would imagine that in an automotive town like this, people are pretty familiar, at least there's a subset of us that are pretty familiar with the graph of a cycloid. And take a look at what functions it's depending on. There's your sine and your cosine. It's just a simple sine and cosine function. So, nice. Really cool.
Why does
All
it
right.
bounce?
Why does it what?
Why does it bounce?
What do you mean, is it bounce? Well, because the point on the rim, I mean, here, let me zoom in a little bit, and then press this again. That point on the rim eventually touches the ground.
Is the equation literally based on a rotating circle?
Yeah, it's literally what's happening is that you have a rim that's rolling, and you got a point on the rim. And let's see, you can see that point on the rim is in orange. And that, if you follow that orange point, that's what's tracing out your curve. So, okay. So there's good applications for this kind of stuff that you're learning. We're just not going to get into something really deep or technical here. This is just kind of a flying survey for you. Let's keep going. I'll let you try one. See what you can come up with. Graphing, example F. You're asked to find same things we did in example D, is get rid of the dependence on T. So you have an equation just in X and Y, and then graph it and show its orientation. So see what you can do. If you're watching at some later point, then you can fast forward until you see the pause button disappear. So the trick we pulled in the last one will help you out in this one in terms of getting rid of the dependence on T. This looks like it should be in a laboratory.
It's like iodine. Looks cool. It looks like iodine.
And you're putting that in your body. Okay. Works for you. Okay. Take that and plug it into. Okay. Well, gotta need the T. Plug that expression in here. Yeah, I know. They're equal, right?
Yeah, you're right.
So my zoomers, you can throw in the expression that you get when you get rid of the dependence on T. Throw that into me in the chat. Thanks, Ben Chang. So the easiest thing to do, I would think, would be to move the 2 to the other side and get y minus 2 equals e to the t. And the big problem with this is that we've got a t here, e to the t, but I've got an expression for e to the t. So if I substitute that expression here into there, then I should be okay. So that gives me x equals 3 times y minus 2, or x equals 3y minus 6. You can solve for y if you want. In fact, you have to solve for y if you're going to graph this on your graphing calculator. That's going to be x minus 6 or x plus 6 equals 3y, or 1/3 x plus 6 equals y. So if you wanted to solve for y and graph it that way, that's great. You could write it one of two ways if you distribute that 1/3. Okay, so that's going to be something with a slope of 1/3 with a y-intercept of 2. One other thing I'll point out here, these are values of t that are greater than 0. E to the t is always a positive expression, so you're never going to get a negative value for x or for y. The graph is going to start out here and then just go up. Actually, you know what? Let's see. At t equals 0, it'd be 3 and 3. So you should start at 3 and 3. Starts at 0 and 3? Let me think that through a little bit more. Equals 0.
0, 2.
It starts at 0, 2.
Yeah. Wait a minute. T equals 0. I'm not. Let's just. It should start at 3, 3. So let's see. Set our window. This time we want T0 to be minimum. 0 to, I don't know, I'm just going to go up to 4. I don't think I want to set it that far. And then my window, I want to see the x-axis and the y-axis. If I hit zoom fit, so here's the thing that is tripping you up. If you hit zoom 0, it's going to adjust your calculator like this. And, you know, that's fine. Let's see, I didn't put in the right equations here yet, though, did I? That's why I'm getting something a little bit different. So let me put in 3 e to the t and 2 plus e to the t. Now let's do zoom 0 again. So this is kind of a good teachable moment. A lot of you are thinking that it starts right at 0, 0 or something else. It doesn't. If you want to get a better look at what's going on down here, let's change our window. Our window does include 0 in the x direction, but it goes way out here. I don't need to see it way out there. Let's go up to maybe 20 by a scale of 5. And in the y direction, well, I like to see the x-axis, so let's put in x equals 0 or put in y equals 0 up to maybe, I don't know, 10? Let's see. Yeah, sure. We'll do 10. So notice your graph does not start at 0, 0, does it? It can't. Why not? If you plug in 0 for t, you get 3 times e to the 0. What's e to the 0? 1. So 3 times 1 would be 1. 3 times 1 would be 3. So the first point here, when t is 0, x is 3. What about y? 2 plus 1 is also going to be 3. So your first point should be at 3 and 3. And then the graph should take off from there. So first point here is at 3 and 3. I should have a line with a slope of 1/3. The only reason I mentioned that is because I eventually want the orientation. Once it's graphed and you're like, oh, I didn't see the orientation, just change t-step to something a little different. So I went from 0.1 to 0.05. That way I can pay attention to how the graph is traced out. It's going to start here at 3, 3 and then move up and to the right with a slope of 1/3. So graphically speaking, I'll put a point, slope of 1/3 over 3 up 1, starting here. And then finally, the orientation, that's just these curves. So there was a question in the chat about the orientation. When you're showing me the orientation, I just want those arrows pointing the direction that this graph gets traced out. Yay.
So that's like all you wanna see on a test, right, is y equals 1/3 x plus 2, and then also graph it, and then the
Yeah.
little arrow.
That's all I'm looking for on the test. Now, hopefully you have a little bit of an idea of how these things work in terms of solving for y, but let me show you, or solving for x and y. But let me show you how to do that back here. Because this one gets all kinds of crazy love when people try and get rid of the x and y. And there's a definite trick to this. So let's take a look back at this and figure out, well, how am I gonna get rid of the x and y? So I have x equals 2 times sine of t, y equals 3 times cosine of t. And I see a lot of people doing some crazy and inventive things with inverse sine, inverse cosine, all kinds of stuff. Let's make it a lot easier. It's going to rely on the one identity that you're going to remember for the rest of your life in this class, or from this class. And we'll get to that in just a second. But for starters, I'm going to do x over t equals sine of t. And y over 3 equals cosine of t. All right. And that got me nowhere. So let me square both sides. And I still don't feel like I'm anywhere, but I can get somewhere from here. And these terms in particular should start setting off little alarm bells for you. A sine squared and a cosine squared. What do you know about sine squared and cosine squared? What was the first identity we learned in this? They add up to 1. So that if I added this plus this, so there's x squared over 2 squared plus y squared over 3 squared, that's like adding sine squared of t plus cosine squared of t, and that equals 1.
That's an ellipse.
Yep, it's an ellipse, which is exactly what we got when we graphed it over here, is an ellipse. So beautiful. It's a nice trick in terms of getting rid of your variables.
On a test, do you want us to tell you what it is, like if it's a parabola, ellipse, hyperbola, whatever?
I'm less worried about that in this class than I would be in a college algebra class. In a college algebra class, you should be able to say, all right, that's an ellipse. You should also be able to find the foci, hint, hint, all right? But in this class, no, just come up with the equation. You should be able to recognize it, but it's not on my priority list to test you on what conic section those things are. Now, I remember my daughter complaining one time about all the crazy stuff she had to memorize for her trig class. And, you know, the unfortunate part is, yeah, there is a lot. But what my suggestion would be is not to memorize everything. So for instance, suppose this is the only trig identity I have memorized out of the Pythagorean theorem. But I need something that involves secant and tangent. What's the tangent in terms of sines and cosines?
Sine over cosine.
Sine of theta over cosine of theta. Okay. So what if, looking at that, I'm like, okay, that's got a denominator of cosine. How about the secant? What's the denominator in the secant?
Cosine?
It's also a cosine. So how about if I take this identity and divide everything by cosine squared? What's that going to look like? Jacqueline, can you help me out on this one? I couldn't quite hear you.
I kind of forgot.
Well, it's kind of here.
Oh. Because it's just tan squared.
All right, tangent squared of theta. Can you do this one? Equals secant squared of theta. Yay. So we've got a new identity. And if I wanted that identity solved for, say, tangent, I could do this. I could say tangent squared of theta equals secant squared of theta minus 1. Or I could put the tangent squared on the other side. What would I get if I put this tangent squared on the other side? How would that look? What identity would I get then? 1 equals what?
Secant squared theta minus tan.
Beautiful. 1 equals secant squared of theta minus tangent squared of theta. Let's keep that one around. All right. So coming back here, I might start thinking about, well, gee, maybe I can use a trick like I did with the previous one. So back here, my trick was to get the x's and y's, or get the sines and cosines by themselves. So what would that look like here? What would be my first step with this one?
Divide by 5.
Sure, divide by 5. X over 5 equals secant of t, and y over 5 equals tangent of t. And that's a good start. All right. Then what? Say again?
X over 5 minus 1.
There's something we got to do before we get to the minus 1 part. We got to square both sides. So x squared over 25 equals secant squared of theta, secant squared of t, and y squared over 25 equals tangent squared of t. Now be careful how you combine these things. What we know from what we just derived is that 1, let's see, so no that this pen is done. Let's see, let's try this. So we know that 1 equals secant squared of theta minus tangent squared of theta. So how do I have to combine these so that I can get rid of the tangent squared and the secant squared?
Subtract them.
If you subtract them. So if I do x squared over 25 minus y squared over 25 equals secant squared of t, secant squared of t minus tangent squared of t, which is 1.
1.
Yep. And in case you're curious, that's a hyperbola. Now when you graph it, you're only going to get one branch of that hyperbola. And I think I've got this one already up for us on Desmos. So let me scroll down to example H. Let's shut off all this other stuff. Get rid of that. Example H. No, that doesn't correspond. Yeah, that's wrong.
Example G.
Oh, here we go, example G. There you go. So the way I did it here is kind of nice because you can see the direction it gets traced out. That would be if I had this zoomed out enough. So you just get a small portion of one branch of that hyperbola. So the full equation, if you wanted to see that one graphed, would be x squared over 25 minus, minus y squared over the same equals 1. So that's the full equation. But we don't have that. We just got a little bit, and we're only tracing out a little portion of that. So right there. Beautiful. All right, comments on that one? Yes, please, Mitchell.
You want us to graph that, or just graph that tiny little bit?
Yeah, that's all that there is to graph because your parameter only goes between 0 and pi over 4. So basically you get up to the point, I don't know, somewhere around, yeah, I have a hard time figuring out whether it'd be like 7 and 5. Yeah.
Do you set the parameters for the, like, you know how you have 0 is less than t that's less than g? How do you put those on Desmos?
So to get this on Desmos, let me just open up another Desmos window. So Desmos, if you wanted to play with this yourself. So let's type this in this way. So you want to type in a point, give it, let's see, coordinates of 5 secant of, I'll use B for Ben, and then 5 tangent of B for Ben. And it says, do you want to put in a slider? Sure. And let's go from 0 to pi over 4. And what I'll do is it'll trace out, well, what's that point going to look like? Or where's that point going to go? All right. And if you want to graph that equation, kind of like what I did, let's see, then you're going to set up something a little bit different. So 5 secant of t, 5 tangent of t, and this time we'll do between 0 and b, and then you get it to trace out like I just did. So kind of cool. So it's something you can do on Desmos, but I think for the most part, in this class, I'm comfortable with you relying more on your graphic calculator because I can't guarantee that your instructors moving forward will be using Desmos. All right, so we're going to split this up into 2 parts, and we'll come back for part 2 in a little bit.